Okay, in this video we're looking at the 6-1 exercises practice, which are problems out of the text. And these primarily deal with perpendicular bisectors, which give us points that are equidistant from the vertices of triangles. Or in other words, gives us the center of a circle that we can inscribe the triangle in or circumscribe the circle about. So let's look and see what's going on with these. So here they wanted to find the distance FM. This is a perpendicular bisector, FK, and point F is equidistant from the two endpoints since on the perpendicular bisector. We can see it's a bisector and it's perpendicular. So this other side must also be 2.8, which is the FM they're looking for. For number 2, they're looking for XW. X is the same distance from W as it is from Y, which is 7.5. And here's the perpendicular bisector. And here, BE is a perpendicular bisector. Well, BE might be a perpendicular bisector. Point E is the same distance from A as it is from F. It is on this ray. Therefore, that makes BE a perpendicular bisector. And BF must also be 4.2. Let's look at this one. What we want to try to do on these is just kind of sketch the perpendicular bisector in and estimate or guesstimate at the intersection. So I want to find the midpoint of this segment, which is about there, and I want to visualize a perpendicular that goes through that midpoint. So there's a perpendicular bisector of this horizontal line. Find the midpoint here. I'm guessing it's right about in there. Perpendicular. It's going to come through there. And for this other side here, the midpoint looks like it's right about in here. And we want to find the intersection. It looks like that would be the intersection. So it kind of looks like 4, 2, excuse me, is the coordinate of the point that's equidistant from those. Let's try to sketch a circle that goes through those. So we got this, got this. Something like that would represent a circle that would have the point 4, 2 as its center, which means that that point 4, 2 is equidistant from each one of those vertices. Same thing for this amusement park. We need to find the perpendicular bisectors. So if we find the midpoint of this side, I think it's right out in there. Try to do a perpendicular. Same thing here. Try to find the midpoint. Do perpendicular down this way. And here, try to find the midpoint. Do perpendicular up and down. It sort of looks like at 0, 2 or 0, 1. We're going to have our circumcenter, which is our point of concurrency. So my estimate is going to be, 1.5, 0, 1.5. Let's see about drawing a circle here. So we want to use this as the center. So I'm going to swing a circle around through here like this. So it does look like right around in here would be the center of that circle. Let's look at the next one. Okay, let's try to do number 17 algebraically. So what we need to do is find the equation of the perpendicular bisector of AB, and then we want to also find the equation of the perpendicular bisector of, say, BC, and we could also do AC, but since we've seen that all these perpendicular bisectors hit in a point of concurrency, just doing 2 of these would probably be enough for us to be able to figure out what's going on. So to find perpendicular, we need to know the slope because the perpendicular is going to be negative reciprocal. And we also need to know the midpoint because it needs to go through that midpoint. So the midpoint of AB, MD AB, is kind of the average of the x's, the average of the y's. So we get 0, 3 from the midpoint. And the midpoint of BC is the average of the x's, average of the y's. We actually get 5, 3. Okay, now we also need to find the slope of AB. So the slope of AB is change in y, change in x. We do 6 minus 0 over 0 minus 0. We get 6 over 0, which is undefined. It means we have a vertical line. And the slope of BC, we do change in y over change in x. We do 0 minus 6, which is minus 6 over 10. So we get minus 3/5 for the slope. Now we want perpendiculars. So the perpendicular of an undefined is going to be a 0 slope, and the slope of a perpendicular for BC is going to be 5/3. So what we're looking for is a line, say for BC, perpendicular bisector, which is going to go through 5, 3 with a slope of 5/3. So we've got a point and a slope. So we want to, let me do this, continue this down here. So we're going to do BC first. So it needs to go through, so if I do point slope form, we have y minus 3 equals the slope, which is 5/3, x minus 5, the x coordinate. I'm going to multiply everything by 3 to get rid of this fraction. 3y minus 9, and then multiply 5 through on everything on the other side because the 3's been canceled out. 5x minus 25. Add 9 to both sides. 3y's is equal to 5x minus 16. And then divide everything by 3. Y equals 5/3 x minus 16/3. So here's the equation of the perpendicular bisector of BC. Now we also want the perpendicular bisector of AB. So it's going to go through the point 0, 3 with a slope of 0. So you do point slope again. Now we're doing AB. So y minus 3 equals 0, x minus 0. So I did point slope for each of those. We get y minus 3 equals 0, y equals 3. So there's our perpendicular bisector of AB. Now the place where these intersect each other is going to be the point of concurrency, or the point that's equidistant. So I need to stick 3 in for y. So we end up with 3 equals 5/3 x minus 16/3. Multiply everything by 3. 9 equals 5x minus 16. Add 16 to both sides. 25 equals 5x. Divide everything by 5. X equals 5. So we got x equals 5, y equals 3. So that's going to be the point of intersection of the perpendicular bisectors, or the point of concurrency of the perpendicular bisectors of this triangle, which is the point that's going to be equidistant from each one of these A, B, and C points. So that's the algebraic method. Let's do number 18 graphically, which will give us an estimate. So to do that, what I need to do is sketch a graph, sketch a grid. Okay, we're sort of sideways a little bit on this. L is at 0, 0, so I need to plot L. K is at 5, -8. 2, 3, 4, 5, 2, 3, 6, 7, 8. It's going to be like down here. And the other point is going to be at 5, 0. 1, 2, 3, 4, 5, 0. So here we have our points. And what we need to do is find the perpendicular bisectors. So the perpendicular bisector of this one side is going to be down through here. The perpendicular bisector of this side is going to be through there like this. And the perpendicular bisector of this side is going to be up through here like this. So approximately here is going to be the end center, which looks as though it's over 1, 2, 3, down 4. So it looks like about 3, -4. Let's see. So with that being the center, let's see what we can do about sketching a circle through here. About like that. So about 3, -4. And again, it's approximate, because the best we can do with the graph without using tools is to get our best guesstimate. Okay, let's look at number 19. They want all the points that are equidistant from C and D. So if we just did this in two dimensions, basically we'd have all these different isosceles type triangle legs, which is going to give us points that kind of line up along this perpendicular bisector. But now if we talk about space, which is 3D, we can actually kind of go back in and out. What that does is actually gives us a disk of points. There's like a cloud of points that all are perpendicular to this axis system. So this disk kind of comes out of the page and goes back into the page and is infinitely thin, like 1 point thick, and it just sits right there in the middle. There's like an infinite disk, and I've got edges drawn, but really this disk has no edge to it. It's just a straight up and down disk that goes on forever. Let's look at number 20. She's got these trees in her yard, so since it's already on the graph, probably the best thing to do would be to sketch this triangle in and then find the perpendicular bisectors of the sides by graphing. So about the middle point here, perpendicular would be a line down through this way. But the midpoint here, perpendicular, would be a line down this way. And the midpoint here, perpendicular, would be a line up this way. So it looks as though right about there is the point of concurrency of those perpendicular bisectors, which will give us the point that's equidistant from each one of these vertices. So it gives the center of a circle, and that is at 0, -2 on the coordinate grid. So that's where she could place her sprinklers, and they're going to be equidistant from each one of those three vertices of the triangular arrangement of the sprinklers. Let's move up. Okay, let's find the error on this one. So Thiago says that that's enough to conclude that K is on the perpendicular bisector. Now, a point that's on the perpendicular bisector is equidistant from the endpoints. It's not showing us that it's equidistant from the endpoints. So is there another way that we can show that this is a perpendicular bisector? It is a bisector because these LJ and JM are marked as congruent to each other, but Is there a way we can prove these two triangles congruent? If we could, then we could say that these are right angles since they're adjacent in a linear pair. But really, this side's congruent to itself. We don't have anything about LK and KM, so we can't use side, side, side. We don't have anything about these two angles being congruent, so we can't use side angle side or hypotenuse leg or anything like that. There's really not enough information for us to know for sure that these triangles are congruent, so we can't really say that these are right angles, which we really can't say then that JK is a perpendicular bisector. It is a bisector, but we can't prove that those are right angles. So Caitlin must be correct. So the next one, we want to write a two-column proof. So let's see what the pattern would be with this. Plane Y is a perpendicular bisector that's going to make these right angles. And AB is going to be a perpendicular bisector, which means that A is going to be equidistant from D and C. That gives us the hypotenuse of this right triangle. There's going to be a right triangle because perpendicular gives us the right angles. And then reflexive, AB is going to be congruent to itself. So this hypotenuse is going to be congruent by hypotenuse leg. And then by corresponding parts, we could say that ADB and ACB are congruent to each other. So that's pretty much how this proof needs to go. So let's see what we can do. So for one, plane Y is perpendicular bisector of DC. That's given. From that, then we can say that AB is perpendicular bisector of DC. This might be a little bit sketchy, but since it's contained in the plane, and the plane is a bisector, I'm just going to put definition of perpendicular bisector. So there may be a better way of getting this perpendicular bisector business in there. Okay, so then, so we got that's the perpendicular bisector. So it gives us that ABD, triangle ABD, and triangle ABC are right triangles. Definition of right triangle. Now we have those are right triangles. That opens up hypotenuse leg. We can say that AC is congruent to AD. Point on perpendicular bisector is equidistant from endpoints. Step 5, AB is congruent to itself, reflexive property. So what this line here does is give us an H for the hypotenuse part of HL. This third step here sets up the right triangle business, which lets us use HL. And AB congruent to AB, that sets up the leg part of the pattern. So for step 6, we can say that triangle ABD is congruent to triangle ABC by HL, hypotenuse leg. And then for 7, we can say that angle ADB is congruent to angle ACB by corresponding parts. Corresponding parts of congruent triangles are congruent. And we've proved what we needed to prove.